Using the table that we've just described, we can now obtain a Boolean equation to represent the output for our bit comparator. We use the ideas from Karnaugh mapping. If you've forgotten them, don't worry, we'll just outline the basic idea. These two bits are ones and can be represented by this product term here. So GN ANDed with not B. These two terms here are handled with the product term GN ANDed with A. And the final product term we have is the product term here, A ANDed with not B, gives us the product term for these two outputs. So this is the simplification we obtain using the ideas from Karnaugh mapping. And the goal of doing this is to have product terms that we can now OR together to obtain the output G out. And we can represent our Boolean equation using the basic gates shown here. So if we take our first term, A ANDed with B bar, here's our A term, here's B, we have not B at this point, so this is B bar. ANDing those two will give us this product term. The next product term, G in B bar, we have G in here and B bar. ANDing those produces this second product term. And then our third product term is generated using this AND gate, and we OR those three terms together using this 3-input OR gate, and that produces our output. When we implement this as a module in Verilog, we're going to need some internal wires, and I've labeled these wires that we need as W1, W2 and W3. There's also another internal wire that we need. It's not labeled here, so I'll just include the label for it. This is an internal wire that we're going to use in our module, and I've called it B inverse, so BINV. Our next step is to implement a module for this comparator. So let's do so. We start with the module keyword. We have to give it a name, so let's call it bit comparator, BITCOMP, and then we've got to list our inputs and outputs. So we've got the input keyword and the inputs A, B, GN, and then we have our outputs, in this case just one, so the output is G out. Close bracket and semicolon. And then we always include an end module keyword. So at this point, what we've done is we've looked at our module from the point of view of inputs and outputs, and we've used that to create the module heading. So if you look at our gate level representation, what we've done is taken the inputs and outputs and use that to define our module heading. And that's always the case. You just need to look at inputs and outputs to get started. We've noted we need some internal wires for our design. We've labeled all those wires B, I and V, W3, W2 and W1. So let's declare those. These are single bits. They're not vectors. So we've got wire B, I, N, V, comma, W1, comma, W2, comma, W3. So these are local declarations that we need inside our module. So when you think about it, at this point in the module, you've got 1, 2, 3, A, B, G in, G out is 4, and then 4 additional wires here. So in total, you've got 8 wires for this module at this point. These are G in, A, B, G out, and then the 4 internal wires, B, I, and V, W1, W2, and W3. Our next step now is to create the gates identified inside our module. The first gate is this inverter here. So not, that's the name of the inverter in the language, the NOT gate. You have to give it a name. I've called it N1, and then we make connections to it. With the built-in gates in Verilog, you cannot use the named port connection. We do that by noting that the output here is BINV, so the first connection is always to the output, so BINV, and then the input to this gate is B, so comma B. So what we've done with this line is created this gate N1 here. Let's look at this AND gate at the bottom of the slide. We use the built-in gate AND. You've got to give it a name. I've called it N2. And the first connection is to the output. The output connects to W1. So that's W1 here, comma. And then you list the inputs. The first input connects to the wire BINV. And the second input connects to A. And close bracket. And I should have a semicolon at the end of each one of these. So this second line here creates this gate and makes the appropriate connections for it. Let's continue, and we'll quickly move through the next two gates. And now we'll look at our last gate, the 3-input OR gate, just the built-in gate OR. We've called it N5. The output of the OR gate connects directly to Gout, so we can use Gout as the output. And then the 3 inputs are W1, W2, and W3. W1, W2, and W3, and terminated with a semicolon. And this statement provides us with this gate here. To summarize, this is our single bit comparator. We have 3 inputs and an output. We then developed a gate level implementation for that functionality, and using that we coded our Verilog implementation shown in yellow. This is the 4-bit comparator that we want to build, and this is our single bit comparator. By drawing this in a slightly different way, it makes it easier to build our 4-bit comparator. So what we'll do is we'll have the inputs coming in from the right and the output going out on the left. So it represents the same block, it's just shown in a different way. And using our 1-bit comparator, we're now going to implement our 4-bit comparator. And remember, our goal is to take the input A, made up of the 4 bits as shown, and compare it with the input B, consisting of these 4 bits, and producing an output G, which is the result of the comparison. To begin, we'll use our single bit comparator to compare these 2 bits using the result from comparing the previous 3 bits of A and B. So we'll feed in A bracket 3 and B bracket 3 into this 1-bit comparator. And we'll feed the result of comparing these 3 bits with these 3 bits to GN. And we can do that in a simple way by now considering 2 3-bit values and using the most significant bits from those 3-bit values to drive another single bit comparator. So for this second single bit comparator, we'll supply A2 and B2. And the input here for GN comes from comparing these 2 bits with these 2 bits. Now the output, Gout, is the result that we get when we compare the 3 bits here with these 3 bits. And that Gout can be used to feed the GN of our first bit comparator. We still need to obtain a GN for our second bit comparator, and we can do that in a similar way. Let's just take these two bits of A and B, and in a similar manner take the most significant bits and provide these as inputs to our third bit comparator. And the output we can now feed in to the next stage. And then to obtain this GN, we end up comparing just two single bits. And we do that by providing A0 and B0 as the two inputs. And because we've no bits left here, we just provide a 0 as the input to GN. And the output of this block now feeds into the input GN of the next block. So what we've done is we've built up our 4-bit comparator using 4 single-bit comparators. And this provides us with our output G. And with this structure, we can now implement our 4-bit comparator. The module starts with the keyword module, the name for the 4-bit comparator, bitcom4. We've got 2 4-bit inputs denoted as follows, and a single bit output G with this line. Let's call this instantiation B3, and you can see we've instantiated B3 on this line. And we make the connections to A, B, GN, and Gout as part of the instantiation. So we connect A3 to small a, and you can see that that's what we require up here. And so on for the remaining connections. Now, you'll note that for GN, we need an internal wire in our design. So what I've done here is I've called that wire GW bracket 2. And locally within the module, you'll note a declaration for GW. It's a 3-bit wire. And the reason it's 3 bits is that we need 3 wires. One for this wire here, another for this one, and another for this one. So we've got GW bracket 1 and GW bracket 0. So these are internal wires inside our module used to connect the output of an instance to the input of another instance. If we take our second instance and label it B2, we've instantiated B2 on this line here, and we've made the resulting connections. And we can do the same for B1, shown here, and then B0 is this instance, and that's on this line. You'll note the connection for GN, we use a 1-bit constant with the constant 0.